Hope everyone's doing okay today. Today we're going to look at I'll try to bring that up on my tablet here. We're going to look at the review for Chapter 9. Good, it's saved. Sorry, I decided I'd rather have it in front of me than to the side. Well, that's the best we're going to do there. Alright. So I got the practice test up in front of me. And I'll be sure to look to the side here for any comments or questions. Test 3 review. So our first problem, we want to find the next two terms for the sequence. I don't know if that's going to work out. And so we have 1 over 5, 3 over 11, 5 over 19, and 7 over 29. And we want to know what those next two terms are. Just got to leave the monitor on. Sorry, guys. Let's see. Display. Screen time. 10 minutes. Okay. That should be better. Okay. So, generally what happens when we have a sequence of terms like this, where it's a fraction, we sometimes look at the numerator and see one sequence, and look at the denominator and see a different sequence. Now in the numerators, we have 1, 3, 5, and 7, so it looks like we're pretty confident in saying 9 and 11 are the numerators for the next two terms, since these are just odd numbers, 1, 3, 5, 7, 9, 11. Now the denominator looks a little bit more tricky. From the denominator, it looks like we have a change of 6, a change of 8, a change of 10, okay? Well, we can see the difference between these values is increasing by 2 each time. So the next one, we should expect to have a change of 12, which would make that a 41, and then a change of 14, which would make that a 55. The main thing in this case is going to be flexibility and thinking and making sure you are able to discern that pattern, whether it's multiplying or adding or adding an increasing value, as in this case. Alright, we have a series here. This one's a geometric series. I don't know if I specifically said geometric, but it is geometric. I'll make sure on the test to call this a geometric series. Anyway, so we want to figure out what R is. Well, R, remember, is the common multiple. Like, is whatever we multiply by 2/3 to equal 1/3, we're going to multiply by that same number times 1, or 2/3 to equal 1/2. We're going to multiply by that same number by 1/2 to get 3/8. Multiply that same number times 3/8 to get 9/32, and so on. We're just going to keep multiplying by the same number, R. So what times 2/3 is 1/2, or what times 1/2 is 3/8, and what times 3/8 is 9/32. Well, I'll tell you right now that because this fraction, 2/3, somehow it gets smaller, but the numbers get smaller here, whereas over here the numbers are getting larger. It's actually going to be a lot easier to figure out what R is looking from here to here than it would be from here to here. Okay? So if we go from 1/2 to 3/8, we think about, okay, what would we have to multiply by to make that happen? Well, 1, we'll have to multiply by a 3 to make it a 3. And 2, we'll have to multiply by a 4 to make it an 8. Now, if the signs are alternating, like plus, minus, we would also make sure either the top or the bottom be a negative. So we would want to keep that in mind also. But we end up, this is all positive, so we know R is equal to 3/8, which is less than 1, so we know it converges. Okay. And because it converges, we have our first value, A, is 2/3. Because it converges, we know the sum is actually equal to A over 1 minus R, and again, that's on the formula sheet. A is 2/3 over 1 minus 3/8. So it's 2/3 divided by 5/8, which is 16/15. So that would be the sum of this series of numbers. So we'll first want to decide if the series is convergent or divergent geometric series, which we see it converges. And then we want from there, if it is convergent, find the sum. That's in the instructions, so we'll go ahead and calculate the sum then. Probably I'm going to give you a convergent series, so you'll then have to find the sum also. Okay. Now, problem 3, we want to use the integral test to determine the convergence or divergence of the series, and we can go ahead and assume it already meets the necessary criteria. Remember when we went over this in the early part of chapter 9, it was 9.3, the criteria it had to meet was that it was it was decreasing positive term, and it had to converge to 0, I believe. Or there might have been another requirement. Decreasing positive term. Anyway, but we had these conditions that we had to check, and so what I'm saying here is don't worry about checking the conditions. This one already meets it. Let's just work the problem. So we're given the summation n equals 1 to infinity n over n squared plus 1 to the 3 halves. Okay, so what we do is we create a function based on this. Now this we call f of n. So our function f of x would just be the same expression but with x instead of n. So we x over x squared plus 1 to the 3 halves. So our integral test says that we want to integrate this function f of x from 1 to infinity, matching what's on the summation. And if this series, or this integral converges, then the series converges. And if this integral diverges, then the series diverges. All we know is that they're going to have the same behavior. So whatever happens with the integral, the same thing will happen with the summation. So now we just have to carry through that integration process. So I want the integral from 1 to infinity of x over x squared plus 1 to 3 halves. Now you might look at this and you start to worry, am I going to have to make a right triangle here? Well, luckily no. We can get away with a simple u substitution instead. Notice that if we let u equals x squared plus 1 here, the derivative of that is 2x, and while we don't have a 2, we do have the x in the numerator, and that's the main thing that we need for the completion of the substitution. So we don't have the 2 though, so we'll say du over 2 is x du. What? dx. That didn't look right at all. Well, sorry, I'm off the screen too, so it's not helping anyway. So du is 2x dx, and then we'll just divide by the 2 so that when we have x times dx here, we'll replace that with du over 2. So we get 1/2 integral du over, and then we'll have u on the bottom to the 3 halves. Okay. So x dx gets replaced by 1/2 du, or du over 2, whichever way we want to express that. And then this inside the parentheses is u, so that's u to the 3 halves now. So we go from there. I'm going to turn over to the next page. So we have 1/2 times the integral du over u to the 3 halves. Now, the way that we would like to integrate that is we can bring that u up to the numerator, so it's to the negative 3 halves. Okay. Which means we can actually integrate that, so it's going to be u to the negative 1/2 divided by negative 1/2. because we add 1 to the exponent and then divide by the new exponent. So, what we have, let's see, we can make that 1/2 times, now it's divided by negative 1/2, so that means it's multiplied by negative 2, multiplied by the reciprocal. And we just simplify from there, so we can make it negative 1 over square root of u. Okay, now u, going back to the previous page, was x squared plus 1. And this is integrated from 1 to infinity. Sorry about that. So if we plug in infinity, now normally we would do this with the limit like we did back in chapter 8. And that t approach infinity and then plug in t, and it's this whole process. But it's actually easy enough, I think, just to think about as if we plug in infinity, what's going to happen here. And there's one of two things that are going to happen. Either it goes to infinity or it goes to 0 when we plug in that infinity. It very rarely does anything else. Sometimes, but not usually. So if infinity gets plugged into the denominator, negative 1 over infinity is 0. If this term had been in the numerator, then infinity is in the numerator and it's just infinity. And so we get 0 minus, and then if you plug in 1, we get negative 1 over the square root of 2. Now, the question is from here, what does this tell us about, first of all, what does this tell us about the integral? Well, if we get a value that's not infinity for the integral, it means the integral converges to this value. Okay? Therefore, the series also converges. Okay. So ultimately what the integral test tells us is that whatever the integral does, the series also does. So if the integral had diverged, then the series would diverge. But they both converge in this case. Okay. Let's move forward to problem 4. Now, problems 4 through 11, each of these we don't know what method to use. So as we go through these, we'll kind of talk about our logic as far as what we're going to choose to use to describe these. So 4, we have the sum, n equals 1 to infinity, of 1 over the third root of 4. 4 into the 4. My bad. 1 over the cube root of n to the 4th power. One thing I cannot do on my little tablet here is zoom. I can zoom a little bit. Okay, there we go. That's a little better. I just can't use the zoom function in Canvas. I can use the tablet's zoom function. Anyway, whenever we just see n to a power here, our first thought should always be p series, which is 1 over n to the p. Okay? So what we'll have to do in this case is, can we write this as n to a power? Well, the third root of n to the fourth, remember that's a fractional exponent, 4 over 3. Because the third root is basically the denominator of this term. 4 would be the exponent, 3 would be the denominator. So we convert that from a radical expression to a fractional exponent. And now we see that p is equal to 4/3. Now, if you remember last time I showed you on the... did I show you? I'm pretty sure I showed you. Yeah, I showed you on the review. I gave you a page, and this will be included on the test, a page with all the different convergence and divergence tests. And for p-series, if you look that up, I can show it to you on the computer. Right here. Here's our p-series. And it says that based on the value of p, it converges when p is greater than 1 and diverges when p is less than or equal to 1. So that's our condition for convergence. Here's our condition for divergence. And so we look at this individual example. P is equal to 4 over 3. That's bigger than 1, so it converges by p-series. Okay. Hopefully this one is pretty straightforward. You do have to be a little bit careful about this, because if we had mixed that up, if we, instead of saying 4 over 3, which is correct, if we had reversed those and said 3 over 4, then we would have arrived at the opposite conclusion here. So, but if I saw what you did, I would only count off for that mistake, not for the other mistake. Okay, problem 5. Sum n equals 2 to infinity of n plus 4 over 2n minus 3. Now, this one, whenever we see a polynomial on the top and on the bottom of the expression, there's really two things that we have in mind. Either one, it is a limit comparison test, or two, it is an nth term test. Now, what actually indicates us which way to go is that if they have the same exponent on top and bottom, we should use the nth term test. If the top has a lower exponent than the bottom, then we can use a comparison test. Okay. But if the numerator has the same exponent here or larger, sorry, my dog's crazy. If we have the same or larger exponent on the numerator, we should use the nth term test. And this is n to the first, and this is n to the first, so that's exactly what we should do here. If the larger exponent's on the bottom, then we'll use the limit comparison test. And we'll talk about that in a second, on number 7. Anyway, so the nth term test can only be used to prove divergence. But it's pretty simple. I mean, all we have to do is take the limit of this expression as n goes to infinity And if the limit is not equal to 0, then it diverges by the nth term test. And that's really all there is to it. Cannot prove convergence, but if the limit is not 0, then it absolutely diverges. What happens here is that we have the same same variable top and bottom, n to the first power. So this is infinity over infinity. So you can either use the shortcut that we talked about, where if they have the same exponent, then the coefficients are actually the limit 1 over 2. Or if we like, we can use L'Hopital's rule, which says we can just differentiate the top and the bottom separately and then get our limit from there, which is still 1 over 2. Okay. But we do get a value that's not equal to 0, therefore it diverges by the nth term test, and that's our justification here. Okay. Picking up garbage in the alley. That's my dog's favorite thing to bark at. It's the garbage man. So I apologize, but he's probably in the back room at the window, I'm sure. Alright, number 6, we have -1 to the nth power, n plus 3 times, divided by the square root of n to the 6 plus 1. Now, because we have -1 to the n, this is our alternating term. So, in this case, we can use an alternating series test. Okay. Oh, sorry. Move that up for you. Anytime we see the alternating term there, at least with these basic series, with not power series, but just our basic series, we know we can use an alternating term test, or alternating series test. And the alternating series test says that if we can show that this function is decreasing and its absolute value, now again we just focus on the non-alternating parts for the alternating series test. So we use n plus 3 over n to the 6 plus 1, and then we want to show it converges to 0 and is decreasing. Is that the two conditions? Yep, those are the two conditions. So it goes to 0 as n goes to infinity, and that it decreases. As long as it meets those two requirements, then it will converge by the alternating series test. And if it doesn't, then we know it does not converge. So first thing we check is, does the limit go to 0? As n goes to infinity. Now, this one's a little bit trickier, but it's not too bad. We know it's infinity over infinity to begin with, because we have n's on top and on bottom. Even the square root doesn't really affect it, really. This is to the 6th power. So we can use L'Hopital's rule. And on top, the derivative is just 1. But on the bottom, since we have n to the 6 plus 1 to the 1/2 power, we use a chain rule, so it's 1/2 times n to the 6 plus 1 to the negative 1/2. Oh, I forgot about that. Yeah. We're going to get stuck in a loop here. Times 6n to the 5th, the derivative inside the parentheses. What happens here, and this is a little silly. Let me move up the page for you. Is we end up rewriting this. And so we get square root of n to the 6 plus 1 on the numerator now over 3n to the 5th on the denominator. And the reality is we haven't really improved our situation from applying L'Hopital's rule. Okay. Here's the shortcut, though. The shortcut says we have n over cube or square root of n to the 6th. We know it's n to the 6 plus 1, but the extra plus 1 doesn't really affect it too much. N to the 6th is really the driving factor here. And the fact that it's a square root of n to the 6 means we actually have n cubed, and then n over n cubed is 1 over n squared. And so the limit as n goes to infinity of 1 over n squared is 0. And that checks out. Okay. So anytime we have that square root expression, if we start using L'Hopital's rule, we're just going to get stuck in a loop doing that and never getting anything besides infinity over infinity. And the terms are going to get increasingly complex in that scenario, which doesn't help us. So instead, what we do is we really look at this in terms of the leading terms. We have n as the first term in the numerator and square root of n to the 6th as the first term on the denominator. Well, we go ahead and take that square root, and then we can simplify, and then we can take our limit. Okay. The other half of this question that we have to prove is that it is decreasing. Usually what we do for decreasing is to show that its derivative is negative. So we have n plus 3 over square root of n to the 6 plus 1, which it might be better to say n to the 6 plus 1 to the 1/2 if we're going to have to differentiate that at some point. So f prime of n, we can say that's equal to, now we take the derivative of the top times the bottom. So derivative of the top is 1 times n to the 6 plus 1 the 1/2 minus the top times the derivative of the bottom, which is 1/2 times n to the 6 plus 1 to the negative 1/2 times 6n to the 5th. And that's all over the denominator squared, which actually just gives us a normal n to the 6 plus 1. To simplify this, I would multiply by n to the 6 plus 1 to the 1/2 on top and bottom. Okay. The reason we do that is that'll make that just to n to the 6 plus 1 to the first, and that will cancel out this term here. So f prime of n equals, let's see, that would be n to the 6 plus 1 minus, and then we'll have n plus 3 times, this will be 1/2, this will go away, and then 6n to the 5th. And on the denominator we'll have n to the 6 plus 1 now to the 3/2 power. From here, it's really just a matter of simplifying what's happening on the numerator. So we get n to the 6 plus 1 minus, and this will be 3n to the 5th distributed to n plus 3. So that's going to give us n to the 6 plus 1 minus 3n to the 6 minus 9 n to the 5th. So that is negative 2 n to the 6 minus 9 n to the 5th plus 1 over n to the 6 plus 1 to the 3/2. Now, the denominator, we can be fairly confident that's a positive number, because if we take any number n, raise it to the 6th power, and add 1, it's still positive. Take a 3/2 root, still positive. Okay, or 3/2 power, still positive. Either way. And then if we take an n to the 6 is positive, times a negative is negative. N to the 5th is positive, times negative 9 is negative. So negative, negative, and the positive 1, that doesn't really change much. I think we can confidently say that is less than 0. Essentially, it ends up being negative over a positive, which is negative. So it converges by the alternating series test. Usually it's not that difficult to check both of those conditions. I'll try to give you a little bit nicer of a summation to work with on the test than this one. This one was pretty rough as far as testing it. Both taking the derivative and finding the limit were unusually difficult. So I'll make sure it doesn't have that square root, and that should make it a lot easier as a result. Okay. So number 7 is next. Sum n equals 0 to infinity. We have n squared plus 3n plus 7 over n squared, n to the 5th, my bad, minus 2n plus 13. Now, remember what I said before when we were talking about the nth term test, and this is kind of a similar situation here that we have here. Okay? We have a polynomial over a polynomial. So in this situation, we either use nth term or the limit comparison test. And that said, we use the nth term test when the exponent on top is the same or larger than the exponent on the bottom. Now, that's not the case here. The bottom actually has a larger exponent. In this case, let's use the limit comparison test if the exponent is larger on the bottom. Okay. And that's what we can do here. Now our limit comparison test, in this one, this is our a sub n. We had to find a summation b sub n to compare it to. Now our comparison is entirely based on these first two terms. N squared over n to the fifth. And so we can reduce that down to 1 over n to the third. Take away 2 from 5. Okay. Now, that's b sub n, 1 over n cubed. Now, we'll notice at this point that b sub n is a p-series. P is equal to 3, which is larger than 1, so it converges. Okay. So essentially we've already established b sub n is 1 over n cubed, and we've also established that that's a convergent p-series because the exponent here is bigger than 1. And that's going to inform us later on what happens to a sub n. But before we can go any further, we have to make sure the limit comparison test actually works here. And so for the limit comparison test, we have to show that 0 is less than the limit as n goes to infinity of a sub n divided by b sub n is less than infinity. It has to be bigger than 0, and it cannot be infinity, so it has to be somewhere in between 0 and infinity. Which seems like a large interval to work with, but it really only works if we choose b sub n correctly. So that's the most vital part, is choosing the correct expression for b sub n. Now, let's find our limit here, and I'll probably go ahead and go to the next page, or the back of this page. So we have a sub n divided by b sub n. So we'll put a sub n first, which is n squared plus 3n plus 7 over n to the 5 minus 2n plus 13. Now we want to divide by b sub n, but instead of dividing by b sub n, let's multiply by its reciprocal. B sub n, remember, was 1 over n cubed, so this will be n cubed over 1. And so we'll go ahead and multiply those. So that distributes the n cubed on the numerator. So it'll be n to the 5 plus 3n to the 4 plus 7n to the third. And on the bottom, multiplying by 1 doesn't change anything, so it's n5 minus 2n plus 13. Now, we look at this as a limit. And again, our shortcut that we talked about was we can just look at the leading terms, n to the 5 over n to the 5. Since they have the same exponent here, then their coefficients ends up being the limit, which is 1 over 1. So we get a limit of 1, which is between 0 and infinity. So the LCT works. Okay. We've established that the limit comparison tests work, but now the question is, well, what does that tell us about a sub n? Well, if LCT works, it means that a sub n has the same behavior as b sub n. And to recall, b sub n, we already said, was a convergent p-series. So since b sub n converges, then so does a sub n. Okay, and that is by the limit comparison test. Okay, number 8 be the sum n equals 1 to infinity 7 to the n over n times 3 to the 2n. Alright. Now, whenever we see a mixture of different terms like this, where we have like a polynomial term n, and we have exponential terms 7 to the n and 3 to the 2n, this is always a ratio test problem that we have to use. Now, if this n wasn't here, it would just be geometric, but with that n there, it is a determining factor. So our ratio test says that, okay, this is a sub n, so you want the limit as n goes to infinity of a sub n plus 1 over a sub n. Well, specifically the absolute value, so we can, if there is an alternating term present, we can ignore it. Okay. So an plus 1, in this case, we just take each of these n's and change them to n plus 1. So it would be 7 to the n plus 1, n plus 1, and then 3 to the 2n plus 2. This is the confusing part for most people, but again, if we take n and replace it by n plus 1, the 2 has to distribute to both of those parts. So 2 times parentheses n plus 1 is 2n plus 2. So now we want to take our limit as n goes to infinity, and we have, let's see, we start with an plus 1, so we'll start with this expression, 7 to the n plus 1 over n plus 1 times 3 to the 2n plus 2 times, instead of dividing by an, we'll multiply by its reciprocal, so there'll be n times 3 to the 2n on top over 7 to the n on bottom. Now, we know that we cannot cancel polynomial terms, although we could reduce them if it's possible. And n over n plus 1, we can't really reduce those. or cancel anything for that matter. So we'll just leave those two alone. The 7s we can certainly reduce, and then the 3s we can reduce. Okay. Again, when we do 7 to the n plus 1 over 7 to the n, that just leaves us 7 to the first over 1. Basically, we have one more 7 on top than we have on bottom, and that's the end result. One more 7 on top than there is on bottom. Similar thing happens with 3 to the 2n over 2n plus 2. The difference is the bottom now has the excess, so it's going to be 1 over, and then we take away 2n from 2n plus 2, it still leaves 3 to the second. Okay, the 2n's cancel, but we still have the 2 there, 3 to the second power. Okay, so that'll be a 7, that'll be a 9. So we'll get 7 times n on the numerator, and on the denominator we'll get n plus 1 times 9. Okay. Well, now let me go to the next page. So we want the limit as n goes to infinity. We'll get 7n on top, and if we distribute on bottom, that'll be 9n plus 9. Now again, our previous statement, with the same exponent top and bottom, then their coefficients will form the limit, 7 over 9. Okay. Now, as far as our interpretation of this result from the limit, remember we called this L. So L is equal to 7 over 9. And we know that it converges if L is less than 1, diverges if L is greater than 1, and is inconclusive L equals 1. Well, 7 over 9 is definitely less than 1, so it converges by the ratio test. Okay. Make sure I had that light on, sorry. It looks a little dark on the screen today for some reason. Anyway. Okay, we'll move forward to, this will be number 9. We have the sum, n equals 0 to infinity, of 28 over 3 to the n. Now, this one is not as difficult as it might seem. I don't know how difficult it seems. It looks relatively simple as far as the term that we're dealing with here. One thing I would like to point out, though, 28 is just a plain number on the numerator. So one thing we can do is factor it out. We don't even have to worry about that 28. It's not going to affect the convergence. It's just an extra multiplier. So what we're instead focused on is 1 over 3 to the n. Well, whenever we have a term like this, like 1 over 3 to the n or similar, we can think of that as 1 to the n over 3 to the n, which we can then say is equal to 1/3 to the nth power. Now with 1/3 to the nth power, that's a geometric series. Any constant to an nth power is geometric. And that's our r value right there in the parentheses, 1/3. R equals 1/3. It's less than 1, so it converges. Okay. That one's actually pretty easy. But we have to recognize the pattern it gives us. And as we see here, 1 over 3 to the n we can rewrite as 1/3 to the n. It turns out to be perfectly acceptable. And then we can just make it geometric from there. Okay. Now problem 10 is also an alternating series, as a second one that we've seen now. -1 to the n times n over n squared minus 3. So what I would recommend is to actually go ahead and use the alternating series test again. I may not give you two of these, but this is in fact the easier of the two, so it's probably the one I'll give you. I don't want to give you that other one. That was a little too much, I think. This should be a much better example of using the alternating series test. So we're going to use f of n is n over n squared minus 3. Notice that we go ahead and omit the alternating term, -1 to the n, and we just work with this one. Again, there's two conditions that this function has to meet. First, we want the limit as n goes to infinity of n over n squared minus 3. The limit has to be 0 in order for this to be a convergent series by the alternating series test. Well, we see that we have a higher exponent on the denominator than we do the numerator, so it does equal 0. So it checks. And here, if you prefer, you could use L'Hopital's rule and it'll work on the first attempt, and it still shows the same outcome. The second one is to show that f of n is decreasing, and again, the way that we typically show that is to show that f prime of n is less than 0. So let's look at f prime. So we take the derivative of the top, which is 1, times the bottom, n squared minus 3, minus the top times the derivative of the bottom, 2n, over the denominator squared. Okay. So that is n squared minus 3 minus n times 2n. over n squared minus 3 squared. Okay. So it's n squared minus 3 minus 2n squared. And if we just keep going, we get f prime of n. N squared minus 2n squared is negative n squared minus 3 over n squared minus 3 squared. So what we have is a negative number on top. These are both negative. And we have a positive number on bottom because this is squared. Any squared number is always positive. And so the result is a negative number, so it's less than 0. So that means it meets both requirements, therefore it converges by the alternating series test. So that's a much better example for that, so I'll probably take out the other problem and just leave this one in. Okay. Let's see. We also have 11. Now 11 we have sum n equals 1 to infinity. No. N factorial over 3n times 2 to the n. Oh, sorry about that, guys. There you go. Now this time we have a polynomial term, 3n, we have an exponential term, 2 to the n, and we have a factorial, n factorial. This is always going to be a ratio test. Okay? Even if we just have any two of those as a ratio test and we happen to have all three. There's no way we can do it any other way. So here's a sub n. So an plus 1 would equal n plus 1 factorial over 3 times n plus 1 times 2 to the n plus 1. And so we find the limit of an plus 1 over an. And if this limit ends up being less than 1, it converges. Greater than 1 diverges, and equals to 1 is inconclusive. Alright, so let's plug in our two expressions now. An plus 1 first, so that is n plus 1 factorial over 3 times n plus 1 times 2 to the n plus 1. And we're dividing by an, so we'll multiply by its reciprocal, of course. 3n times 2 to the n over n factorial. Okay. Now, there are several things that we can reduce or simplify here. First of all, we have n plus 1 factorial over n factorial. The shortcut here is to find the smallest of the two. N is the smallest of the two. So we know that this one's going to cancel out entirely. And then whatever comes after n until we get to this number, n plus 1. Well, the next term after n is n plus 1. So this can be n plus 1 over 1. So if this was n plus 2 over n factorial, then after n it would be n plus 1 times n plus 2. And we put both of those on top over 1. So it's just a matter of how much one expression exceeds the other one by. Alright, 3n over 3 times n plus 1. Turns out we can actually reduce the 3's out of this equation, or cancel the 3's out of the equation. So this is n over n plus 1. And then 2 to the n over 2 to the n plus 1 is 1 over 2, because we have one more 2 on the bottom than we do on the top. So n takes away this n, but we still have 2 to the first down here. So it's 1 over 2. Anyway, so putting that together, on the top we have n plus 1, n, and 1. And on the bottom we have 1, n plus 1, and 2. Okay. Now, here we can actually reduce these n plus 1's that we now have. Okay, because we have an n plus 1 on top and bottom, we just cancel those out. So we look at what's left, putting those together. We have n over 2. And so now we go ahead and take that limit as n goes to infinity. So we have infinity over 2, which is still infinity. So this one actually diverges by the ratio test. Okay. So that gets us from 4 through 11, takes care of those. And again, we didn't know, we weren't told in the questions which method to use, so hopefully I've informed you a bit as far as how we could choose which one to use based on what it looks like. Ratio test, like we said, ends up using a combination of 2 or more different types of expressions, which would be polynomials, exponential terms, and then factorial terms. Nth term test and LCT is basically when we have a polynomial or a polynomial, but it depends on those exponents which one we end up using, and we talked about that already. Alternating series test is pretty obvious because there's an alternating term, -1 to the n, or similar, that is present in the expression. And geometric is just a constant raised to the nth power. Did we look at anything else? Oh, we had our p-series also, but again, p is pretty straightforward, p-series, because we end up with 1 over n to the p power. So anytime we have n to raised to a power, that's a p-series test. Okay. Let's move on to 12. If f of x equals e to the 2x minus 4, we want a Taylor polynomial for f of x centered at x equals 2 and using n equals 4. Now, you have the formula for this back on the formula sheet for this section, or this test, or review, whatever it is we're doing now. And I'll be sure to include the same on the exam. What we do for a polynomial, notice that we want we want n equals 4. That means we'll start with the f of x, f prime of x, and we're going to need 4 derivatives here. Which means we end up with 5 terms altogether. Alright, so f of x is e to the 2x minus 4. Now, when we take the derivative, f prime of x, remember with their exponentials, the exponential part stays the same, and we multiply by the derivative of the exponent. So we keep e to the 2x minus 4, and the derivative of 2x minus 4 is 2. So what ultimately happens here is each time we differentiate, we're going to multiply by this 2 from the exponent. So the next one will be 4 e to the 2x minus 4. The next one will be 8 e to the 2x minus 4. And the last one will be 16 e to the 2x minus 4. So that's our 5 functions we have to look at, and what we want to do is plug in the center, in this case x equals 2, to each of these 5 functions. So f of 2 will be e to the 2 times 2 minus 4. That's just e to the 0, so 1. F prime of 2, we're going to get 2 e to the 0. So that's 2. F double prime of 2, we get 4 e to the 0, which is 4. Third derivative, evaluated at 2, will give us 8 e to the 0, which is 8. And then the fourth derivative, evaluated at 2, will be 16 times e to the 0, or just 16. So we get each of those values. Now, our fourth Taylor polynomial is going to be f of c. C is the center value, so I'll use the generic formula, and then we'll plug in all the values in the next step. Then f prime of c times x minus c. F double prime, whoops, a little carried away there, sorry. F double prime of c times x minus c squared over 2 factorial. Third derivative at c times x minus c cubed over 3 factorial. And get a little bit off screen, I think we'll be okay there. Plus fourth derivative at c times x minus c to the 4th over 4 factorial. Okay. And we have each of these values here already. F of 2, f prime 2, f double prime 2. So we'll plug those in for f of c values for each of the derivatives. And c is 2. Well, we already established that, so we'll plug that in for c here also. Let's see, here. So p4 of x, that's the fourth polynomial, or fourth Taylor polynomial in this case. So start f of c, which is 1, f prime of c, which is 2, times x minus 2, f double prime c, which is 4, times x minus 2 squared over 2 factorial is 4, or 2 on the bottom, sorry. I wrote down a 2 and then I said 4, so I have no idea what I'm doing. Third derivative at 2 is 8. So 8 times x minus 2 to the third. 3 factorial is 6. And then P4, the fourth derivative of f at c is 16. X minus 2 to the fourth. And then 4 factorial is 24. Okay. So that, I shouldn't have put a box around it. We have to reduce still. Look at that. Those are all reducible. Anyway, P4 of x. Let's go through and reduce. We don't have to worry about like distributing these things or anything. Don't worry about that. But go ahead and reduce at least. So this will be 2 x minus 2 squared, 4 thirds, x minus 2 cubed, and then 2 thirds, x minus 2 to the fourth. That's our correct expression. Oh, crap. That's our correct expression. Okay. So that's our polynomial. And now, the other part of the question is test the accuracy. We'll find P4 of 2.5, which should approximate the value of e to the first, if we've done it correctly. Okay. So B, P4 of 2.5, so it's 1 plus 2. Now, if we plug in 2.5 for x, 2.5 minus 2 is just 0.5. Then 2.5 squared plus 4 thirds, 0.5 to the third, and then plus 2 thirds times 0.5 to the fourth. Because 2.5 minus 2 is 0.5 in each of these cases. We just have to make sure we calculate everything beyond that. So. Alright. Some of this we can do by hand, but not all of it. So this would be 1. 2 times 0.5 is 1. 0.5 squared is 0.25. 0.5 to the third is 0.125. And 0.5 to the fourth is 0.0625. Yes. Let's just put all those together now. I'll do the rest with the calculator. I don't want to do those on hand. Anyway, we get 2. This is 2.5 right here, these first 3 terms, because that's 0.5. So we start with for 2.5. For plus, and we get 4 over 3 times 0.125 plus, parentheses, 2 over 3 times 0.0625. So we get 2.708333, etc. Now, the question reads, test the accuracy of the polynomial by finding the value of P4 at 2.5 and comparing it to the actual value of e to the first. The reason it's e to the first is if we look at f of 2.5, that is e to the 2 times 2.5 minus 4. So it's e to the 5 minus 4, which is e to the first. And e to the first, from our calculator, also known as e, is 2.7182818. Okay. I kind of anticlimactic there. Anyway, we see we're actually, it's not a bad approximation just yet. It was centered at 2, which means it should be accurate for values near 2. And 2.5 is relatively close to 2, although it turns out that maybe not as accurate as we would like to be, but it is pretty close. I mean, we're basically 1/100th off from the answer, give or take. So, not a terrible approximation. We know it's not going to be perfect, especially the way e works, but you know, at least it tells us that the answer we got here, we must have done that correctly because it should be pretty close to this answer. Okay, that's really what that's informing us, is that, you know, even though it's not the same, we know that we've got a pretty good approximation. All right. Continuing from there. Problem 13. Here we just want to find the radius of convergence of the power series. So we have x to the n over n plus 1 factorial. Now, what we did is we call this u sub n, and the way that we proceed is we want the limit as n goes to infinity of absolute value of u sub n plus 1 over u sub n, and find the values of x for when that limit is less than 1. This is called the ratio test for power series, because remember, the ratio test only converged when it was less than 1. That's really the same outcome we're looking for here. The difference is we're not just deciding if it is less than 1, we're deciding for which values is it less than 1. So there's a slight difference because of that. Alright. Moving right along. So un plus 1 is going to be x to the n plus 1 over n plus 2 factorial. That just adds an extra 1 to that. And so, similar to how we did the ratio test problems before, we'll do un plus 1 times the reciprocal of un. And this is inside the absolute value. So x to the n plus 1 over n plus 2 factorial times n plus 1 factorial over x to the n. This has to be less than 1. Now in both of these cases we can reduce with the x's and with the factorial expressions. X to the n plus 1 over x to the n is just equal to x. Technically that does carry the absolute value. The factorial terms we don't worry about the absolute value because those are automatically positive. And then n plus 1 factorial divided by n plus 2 factorial. Again, n plus 1 factorial gets all the numbers from 1 to n plus 1 multiplied together. And the bottom, the denominator, has all the same values, but then it goes one step further. You know, after n plus 1, it goes to n plus 2. So we only have that one additional term on the denominator, n plus 2, that won't be canceled out in this scenario. Everything else will cancel out. Okay, so now we can use that to create the limit, or find the limit now. Use the back of this previous page that I didn't use. Let's see. There we go. A little bit lower. There we are. So it's limit n go to infinity. Let's see, and we had simplified what's here. We have absolute value, and we just have x over n plus 2, and we want to know when that's less than 1. Now, n is already going to be a positive number. N is a positive number that's approaching infinity. X, however, can have positive or negative values. We don't know yet. So what we can do is we can change it to this. We can take out the absolute value of x because the limit is only as n goes to infinity. So x is not affected by n, so we can just freely move it in and out of this limit if we want to. And this time we want to move it out. N plus 2, however, has to stay there because it is affected by the value of n. It's part of that expression. Okay, but notice that we now just leave this as parentheses because n is already a positive number. So this result is automatically positive. This is the only one that may now have negative values. That's what we worry about here. So, the question is now, what is the value of this limit? Well, our limit, 1 over infinity, goes to 0. Anytime we have infinity on the denominator, it's going to be a 0 value. So we have the absolute value of x times 0 is less than 1. Which absolute value of x times 0 is just 0. Doesn't matter what x is. If it's multiplied by 0, it's going to be 0. And 0 is less than 1, so the question is really, for which values of x will 0 always be less than 1? Well, 0 is always less than 1. These are just whole numbers. There's no x's here. And so this is true for all x. We could say negative infinity to infinity is our radius or interval of convergence. Gotcha. Okay. Nope. There we go. All of a sudden, the tablet didn't want to cooperate. Now, as you might expect, we're going to get a little bit different outcome for our second problem here. Which is 14. We have the sum, n equals 0 to infinity, negative 1 to the n times x minus 3 to the n. This will be over n times 2 to the n. All right. Now, same problem that we just worked, or same as the problem that we just worked. We want to find the radius of convergence, or the interval of convergence for x in this power series. Now again, we're going to let this be u sub n. Now, we actually will leave out the negative 1 to the n because we know that we're using the absolute value. So negative 1 to the n is either negative or positive 1, but if we take the absolute value, it's all positive 1s. Multiplying by positive 1s doesn't change anything. So, effectively, we'll say u sub n is x minus 3 Or we could say it like this: absolute value of e sub n is x minus 3 to the n over n times 2 to the n. And then un plus 1, just plug in n plus 1 for n, so x minus 3 to the n plus 1 over n plus 1 times 2 to the n plus 1. All right. So we start with n plus 1, so x minus 3 to the n plus 1 over n plus 1 times 2 to the n plus 1 times the reciprocal of un, which is n times 2 to the n over x minus 3 to the n. And we want this to be less than 1. Now, the x minus 3's, we have n plus 1 over n. That's just going to leave a single x minus 3 to the first over 1. Our 2 to the n's, 2 to the n over 2 to the n plus 1. We actually have one more on the bottom than we have on top. So it's 1 over 2 to the first. And then n over n plus 1 cannot be simplified. We cannot cancel parts of polynomials without canceling the entire term, or entire factor of the term. Okay. Get a drink. So, let's see. Now we'll have limit as n goes to infinity. And inside, on top, we'll have x minus 3, n, and 1. On bottom, we'll have a 1, or n plus 1 times 2 times 1. Okay. So that's where we're at. Now, again, the only things that have to stay inside the limit are the things that have n's, which is n over n plus 1. So the x minus 3 and the 2, we can pull outside the limit if we like. So x minus 3 over 2. This is an absolute value. We cannot get rid of the absolute value because x may be positive or negative. And then limit n go to infinity. Inside we'll have n over n plus 1. Multiplied by 1, of course, doesn't change anything. And this is less than 1. Okay, so now we look at our value of our limit here. We have the same exponent on top and bottom, or if we apply L'Hopital's rule, either way, the limit is 1. 1 over 1. Okay, so we end up with the absolute value of x minus 3 over 2 is less than 1. Well, we can turn that into an inequality. We can say, well, x minus 3 over 2 must be between negative 1 and positive 1. Anytime we have the absolute value less than 1, that's our interpretation. The expression must be between negative and positive of that number, 1, that's the case. And, from here we just solve for x in the middle. So you can multiply everything by 2. and then add 3 to everything. So 1 is less than x is less than 5. Okay. We still have 3 problems left, and we're about 12 minutes from the end of class, so probably I'll just keep going because I want to make sure I finish this video today. That way you have everything that you need. But remember on Tuesday, because we're taking a test, we do not have a class scheduled for Tuesday next week, or Thursday because of the holiday. So if you wanted to take the test on Tuesday, I would recommend that. That would actually be a very good time to take it. I'll give you a 3-hour window, or 3-hour time limit. It's a little bit longer test, and each one of these is basically you have to upload a file. That way we can have a little leeway as far as any technical difficulties go. But I'll ultimately give you from today, when I get the test uploaded and ready to go, which will be this afternoon, anytime this afternoon through Monday after Thanksgiving, we'll have to take the test. So if you wanted to wait until after Thanksgiving, and you could do that, I would suggest Tuesday, though, because everything will hopefully still be fresh, and you'll be able to just take it during normal class time, and then you'll be done with it, and you don't have to worry about anything over the holiday. That's probably the best way to go. But again, I can give you some options. All right, but let's finish this review. I don't want to leave an unfinished review. That would be silly. But like I said, it'll take a little bit longer than we have until the end of class, so I apologize for that. That's also why I'm giving you a little bit more time in this test than the previous ones. Okay, for these problems, these are like what we worked on Tuesday this week. These last 3 questions are from Tuesday's class. Which is finding the first two, 15 and 16, find the power series for the given functions centered at the given value. So at this time, if f of x is 3 over 1 minus 2x, centered at 0. So this one's actually pretty straightforward. Because remember, what we really want is a 1 on top and on bottom in that first position there. We already have that 1, so we're good. Just to make this a 1, we just have to factor a 3 out. Thankfully, it's centered at 0. Okay. Now, we have a power series. No, this is 1 over 1 minus f of x. I'm going to give you this formula on the formula sheet. I don't quite believe I gave you all of these on the practice test, but we talked about it in class on Tuesday. 1 over 1 minus f of x is the sum, n equals 0 to infinity, of that function raised to the nth power. So there'll be 2x to the nth power. And that's it. That's our answer right there. Centered at 0 is generally not too hard, and we did several examples on Tuesday like that, where the differing degrees of difficulty. Like if there was a 2 here instead of a 1, we just have to factor a 2 out of everything on the bottom. It's not a huge deal, but it does make some changes. We have to make sure we account for those changes. Now 16, we do have a little bit of a different situation because it's centered at -1. Well, if it's centered at -1, okay, 4, we know that's going to be the numerator. We're going to have x minus the center right here. So x minus negative 1 would be an x plus 1. So the question is, how does this first number have to change to accommodate that extra number we've added here? Added or subtracted. And a lot of it depends on whether this is a plus or minus. So we went from an x to an x plus 1 to account for the center. So we want this to be x minus the center, which is x plus 1. I'm kind of repeating myself, but I want to make sure it's clear. So we did that change. Now, the question is, whatever number we write here, when these are combined back together, should equal 2 plus x. Because we're not changing this function, we're just changing how it looks to fit a certain pattern. Okay. And so, if this is a plus 1 and this is a plus here, so all we've done is we've added 1 here. So to balance out our addition of 1, we then subtract 1 here and make that a 1. Notice if we combine this back together, 1 plus x plus 1 gives us 2 plus x. Well, we want it in this form specifically, and now the 4, we can bring that out. Notice how this sets up exactly what we want here. We took out the 4, so now we have a 1 on the numerator, a 1 in this first position on the denominator, and then our expression. Now, this one also has a plus between the terms rather than a minus. Now, a minus, as we saw in 15, just goes to 2x to the, whatever that function is, to the nth power. So we'll still have this function to the nth power, but because it's plus, we're also going to have negative 1 to the n. Okay. So we end up with 4 times the sum, n equals 0 to infinity, negative 1 to the n times x plus 1 to the nth power. Alright. So you use those two examples, use the examples from Tuesday's class, and that should serve you well going into this exam for these two questions. Alright. Number 17. This is our last problem, so we're actually not too bad. This will take a little bit of work, though. Now remember that I told you on Tuesday there is a consecutive typos in this, and I'll make sure I correct it when I write it down here. So I apologize for that. Not just one typo, but a whole group of them. But I said over here, or underneath it on the page, x squared over 1 plus x. Now what I meant to write was this identical expression, x squared over 1 plus x to the 6th, is equal to the sum, n equals 0 to infinity, negative 1 to the n, x to the 6n plus 2. What I did last time, if you look at the review, I left off those 6's, so I apologize for that. Although what I wrote was technically correct, it's just not what I wanted to write. Anyway, I think you'll be fine if creating a power series from this, but because we already did it twice, I just made that part easier at least, so it could still focus on the actual approximation of this integral. Now I did mention that the approximate value is 0.11014. We'll see how close we get to that. We said using the first 4 terms of the series. Okay. Alright, so this will equal the integral 0 to 0.7. And we'll replace x squared over 1 plus x to the 6th with the summation that is equivalent. So sum n equals 0 to infinity, negative 1 to the n, x to the 6n plus 2 dx. So we have to integrate the power series, which is ultimately what we're trying to do here. So don't need that. For integrating, we don't need that. New bracket. Here we go. So we integrate the power series. N equals 0, infinity, of negative 1 to the n. Now, we're integrating with respect to x, so it's really only the term that has x in it that we're concerned with integrating. X to the 6n plus 2 becomes x to the 6n plus 3. And then we'll divide by this new exponent, 6n plus 3. And so that gives us 0 to 0.7 as our limits of integration. Now, we'll plug in our limits of integration. So plug in 0.7 first. I have a feeling this one's not going to be that accurate, but we'll see how it goes. And then we'll plug in the 0. And what happens when we have that 0 right there? Putting 0 in like this basically zeroes out the whole thing. Okay, so we didn't even have to worry about calculating that term if we plug in the 0, which is why when we look at these problems, they're always from 0 to some value close to 0. 1, because they're centered at 0, and so that in a closer value to 0 will be more accurate. And 2, because the 0 being plugged in, since it's the center, automatically zeroes out the whole thing, which is great for our purposes at least. So now we just have to approximate this power series using the first 4 terms of that series. Okay. So n equals 0, n equals 1, n equals 2, and n equals 3. When it says 4 terms, n equals 0 counts as the first term, so 1, 2, 3, 4. So we plug in 0 for n, first of all. Negative 1 to the 0 is 1, positive. 0.7 to the 6 times 0 plus 3, so it's the third power. 0.7 to the third power. I'm going to put that on the calculator real quick, so I'm going to forget. So we get 0.7 to the third. And then we'll divide by 6 times 0 plus 3, so divide by 3. So we get 0.11433. I'll go to 6 decimal places here. 11433. The reason I want to go to 6 decimal places is I've given the approximate value to 5 places, so we'll go 1 place further and then we'll be able to compare it from there. Alright, n equals 1. So that'll be negative 1 to the first, which is definitely a negative 1. N equals 1 here. 6 times 1 plus 3 is 9. So it'll be 0.7 to the 9 divided by 9. So 0.7 to the 9th power, wow, divided by 9, sorry, 0.004484. Okay, n equals 2. Negative 1 squared will give us a positive. And these numbers are the same, so 6 times 2 is 12, plus 3 is 15. So 0.7 to the 15 over 15. So 0.000317. Okay. And for n equals 3, negative 1 to the third is negative. 6 times 3 is 18, plus 3 is 21. So 0.7 to the 21st power divided by 21. So that is 4 zeros and then 2 7 after we round. Okay. So now we'll just put each of these together. Actually, it may be pretty accurate because we got 4 leading zeros here. 0.114333 minus 0.004484 plus 0.000317 minus 0.000027. So we get 0.110139. And we said the actual value, approximate real value. I'll figure it out, sorry. It's 0.11014. That is darn close to that. So that actually came out more accurate than I expected. When we get 4 leading zeros like this, we anticipate our answer is at least accurate to the 4th decimal place. Maybe further, but that's a guarantee of at least 4 places of accuracy. This one looks like if we round, we'll get exactly the same number if we round here. I don't remember how I got that value, 0.11014. I think it's possible to integrate that expression and not just calculate it by hand. I don't remember, it might have been an arctangent. Yeah, it's like arctangent of x cubed divided by 3. Something like that. Anyway. But yeah, that's really close. Pretty good deal there. I'll be sure to give you an approximation to aim towards on your work on the exam as well. So you'll definitely have that available, so don't worry about that. And I'll go ahead and post a link to this video in our or as an announcement in Canvas when I finish the test and get it uploaded, just to let you know, 1, the test is ready, and 2, here's a link to the review for anyone that needed to watch it or rewatch it. So, alright, so y'all have well shoot, I won't see you at all next week, so have a good Thanksgiving. Enjoy the time off. That'll be great for all of us, I think. And good luck on the tests. And I'll be sure, like I said, to make an announcement in a little while once I get everything. The difficult thing for me making this exam in Canvas is having to typeset all the summations. It's kind of a pain in the backside. So anyway, it may take a little while. I apologize, but I have my office hours coming up, so I have that time available. So, y'all take care. Enjoy the holidays. Enjoy being with your family. Hopefully not too big of a gathering, just for safety's sake. But take care, and I will see you Tuesday after Thanksgiving, and we'll look at a little bit of Chapter 10, and then we'll review for the final. So y'all take care. Bye.